This is SEDA Solar's first event of this year, of which there'll be 4, and we will be telling you more about it later on. We're very lucky today to have Richard Atkins, Emmanuel Shitu, and Charlie Farrell with us as our provocateurs to engage us in this very interesting discussion on energy consumption, on how much embodied energy and emissions there is in our current mode of energy use in Scotland, as well as how to move towards cleaner, environmentally friendly, sustainable design, and whether that actually works or not in life cycle analysis assessment, and how real those numbers that is bantered about is, or are rather, and also talk about the long-term effects of having these technologies. So, you know, as the population increases and our energy demand is increasing to almost double current energy consumption by 2035, then we're installing all these PVs, and then there's a waste stream issue. And so at some point, there'll be a recycling issue as well, if we're going down the circular economy route, and what that means in terms of resources, raw materials, and all of that. So hopefully we'll go in full circle from Richard's talk to Emmanuel's talk to Charlie's talk, from all the way from energy sources, raw materials, life cycle analysis to recycling as a full circle. So without further ado, if I could remind you all to mute yourselves and turn off your cameras if you're not speaking, so to make the best recording possible for everyone for afterwards, for if you want to rewatch it. Without further ado, I shall pass on to Richard, our first speaker.
Okay. Hello, everybody. Thank you, Gloria, for that opening to the today's event. And I shall just try and make sure I can share my screen. There we go. Right. Hopefully, everybody can see that. I can't see anyone nodding, but no one's saying they can't. So I'm hoping you can see the front slide. We've all been asked to introduce ourselves. My name is Richard Atkins. I'm a practicing architect. I wear probably too many hats. I'm a former chair of SEDA. I've had various roles over the years with the RAS. I currently sit on the governance and practice committees, and I also represent the RAS on the Section 6 working group for the Building Standards Division. And we've been looking at and discussing upcoming changes to Section 6, which I can't tell you lots about, but there will be a consultation coming along soon, and obviously I hope everybody will take notice of that and think about the what's proposed and respond to the questionnaires. I also have an involvement in a community wind farm that's partly owned by Berwickshire Housing Association, and I've learned a lot about wind power over the years. I've also got my own PVs on the roof, and I've had those for about 5 or 6 years now. I'm very happy with those and what they've done. And finally, the subject of my PhD was looking at the assessment of social, financial, and environmental sustainability in the existing built environment. So apologies for boring you with a long list of different hats, but I hope that shows that I'm hopefully coming from these sort of issues from multiple different directions. And I suppose one of the things I'd like to get over today is in any aspect of sustainability, any aspect of an intervention in the built environment, but very true of photovoltaics, there are numerous aspects to weigh up. And oops, thought that might give me the first slide. Here we go. It's very good to look at numbers and weigh up numbers, but again, part of what I'd like to get across is always be aware that numbers can change, and also not be afraid to go with your own intuitive understanding of what you think is the best solution. So let's start at the beginning. In terms of photovoltaics, oops, people sending me email. I mean, it's a fantastic industry when you think about it. What other industry could you be involved in which your raw material, sunshine, arrives free at the factory door? You don't really need a workforce, bit occasional maintenance. You don't have any cost to transport your product to the customer. There's no sales, there's no advertising, you don't need a guarantee. It's unlikely to be returned, and it's very unlikely to fail in use. It's all really good news. But as I was starting to say before, oops, we need to think a little bit about the statistics that go with this. And we'll delve into some of those, all of which are potentially open to question. They always say that, you know, the only thing you can prove with statistics is you can prove anything with statistics. But I think it's particularly true in the electricity market, which is highly dynamic. So the carbon footprint of generation can be changing, in fact, is reconciled every half an hour in the electricity industry. But it's transforming radically over time. And many of the numbers I will be giving you will by definition, have been out of date when I found them. Oops. And of course, most statistics are made up anyway, aren't they? So let's think a little bit about the energy payback period for PVs. And I'm hoping two other speakers, Charlie and Manuel, will be able to flesh some of this out, because I'm presenting some numbers, but these numbers are the numbers I've found. So they're always, I think, open to challenge, and we should invite that challenge, because it's all about understanding more, finding out, and keeping up to date. I suppose keeping up to date is the main point I want to make. So how much energy does it take to make some PVs? Well, for a 1 peak kilowatt array is probably 4 panels, maybe a little bit less than 4 panels. Panels will go from about 250 watts to, you can get them up to 500, but the sort of common ones are around about the 300 mark. And if you put them on a south-facing roof in Scotland at 30 degrees and it's not overshadowed, according to SAP, which is standard assessment procedure for assessing these things in new domestic buildings, and we should take that with a pinch of salt, but according to that, you'll get about 860 kilowatts per year in terms of energy coming off them. They'll take about 4,000 to make. So that gives a payback of about 4.5 years. And this is taken from the paper that's referenced below. So it's a peer-reviewed paper. I hope that's a reasonable number, but like I say, all of these numbers are open to challenge, I think. But 4.5 years seems pretty reasonable in terms of energy payback. But what about the carbon? Well, of course, that depends on the numbers you use. So first of all, let's have a look at the UK emission factors. And again, these are taken from SAP 2012. There we go. Those numbers, I think, will remain fairly stable in terms of a SAP calculation. Again, I'm assuming these are based on reasonable amounts of research within the various industries. Intuitively, the carbon footprint of these things isn't going to change that much over time. But what about electricity? And this gets a bit more complex. So according to SAP, the carbon footprint is about 0.5 kilogram per kilowatt hour. And we're still using that metric. And you can see that's from SAP 2012, which is already 9 years old. But that number was set probably a few years before that in the consultation. There was a consultation on the next version of SAP, which will come in with the next version of the regulations, in fact, about 3 years ago, and it suggested more than halving that. There's been a more recent one, which has suggested halving that again. But what are the figures in reality? Well, according to the UK government, the most recent numbers I could find from 2019, so again, already out of date, it is not far away from what was originally proposed in the next version of SAP. For Scotland, however, our grid, and this is a 2017 figure, is about 1/10 of that. So the Scottish grid is virtually decarbonised already. What about China? Well, that's a good question, and I found finding the answer to that quite difficult. Why am I interested in the carbon footprint of China or the Chinese grid? Well, I think 2/3 or possibly more of the PV panels produced in the world are currently produced in China. I did manage to find a paper from 2020 which was looking at the makeup of the electricity grid in China, and that suggests that their electricity grid is about 3 times as heavy, if you like, or has a footprint 3 times the size of the UK grid, which is about 30 times the Scottish grid. Now, of course, that doesn't necessarily mean that PVs are made only using electrical energy, and I'm hoping that Emmanuel in particular might be able to throw some light on that. But it does suggest that it's a considerably greater carbon footprint. And of course, if you do the multiplier of that, you get to a fairly frightening 145 years if you're comparing the CO2 emissions factor in Scotland with that in China. Like I say, all of these numbers are open to question. And I might be out to buy a, I don't know, factor of 2, 3, 4, 5, who knows? But one of the points I want to get across is we don't have time for a payback. And again, one of the things that particularly exercises me is when you see projects, which are often lovely architectural projects, really nice, but they're a project with somebody saying, I've decided to build myself an eco house, a term I absolutely loathe, but an eco house. And I'm building it out of concrete and I'm surrounding it with polystyrene insulation and I'm putting PVs on the roof and therefore I'll have no energy bills and I'll create no carbon. Isn't this wonderful? And I look at that and think of all of the carbon emissions associated with the concrete and the polystyrene and the PVs and think, you may have a zero emissions building in use, but you could have a payback period of 10, 20, 40, 100 years. If you think about the carbon footprint of electricity for Scotland, it's potentially an infinite payback period. You're actually putting a lot of carbon into the atmosphere right now, and right now is when we don't need it. We don't have time for that payback. So Scotland's exports around 1/3 of its near zero emissions. So in a sense, do we need to do any more? Well, yeah, we certainly do, because 78% of the energy that we use in Scotland is still fossil fuel based, and that's mainly heating for buildings and transport. So even though we have a very low capacity, very low emissions grid, and we're not using all the electricity inside Scotland, and that's another debate about whether we should count just Scotland or the UK or Europe or how big your grid gets, we actually still need more. So should we just meet that with wind farms and tidal and hydro? Well, yes. Equally importantly, we should make buildings and vehicles much more efficient. But there's 2 other factors there. Firstly, the district electrical network system was never designed to distribute that much electricity. It was built on the basis that most homes would be using fossil fuels. So there's a very great danger that the network goes bang if you try to put too much electricity down it. So we do need PVs, and we do need things like electrical storage and other forms of heat storage in homes in order to smooth out the demand and supply curves. So we're not trying to push too much power or more power down the network than we can cope. But also all those other things have their own embodied carbon footprint. A wind farm requires to be manufactured and installed, and the same with tidal. And if you put insulation into a building, Some forms of insulation may have an element of carbon sequestration, if you're happy to accept that argument. But a lot of the insulation, and in fact probably the majority of the insulation that's currently used for retrofit, has its own carbon footprint. So PV, it has to still be part of the solution. But are there other paybacks that we should be looking at, or what are the paybacks we should be looking at? Well, energy, I think to my mind is obvious, partly because it's less complex than carbon, because you've taken out the carbon emissions factor for the energy used to manufacture things in different places and move them about and then transport them and then bring them to the UK and then take them and put them on the roof. And intuitively, it promotes more efficient panels being made more efficiently. And I was reading an article in the last day or so that was actually suggesting that one of the issues with the market dominance of PVs coming from China is that has, because the cost of PVs has gone down so significantly, which on one level is great, but it's been a disincentive to develop more efficient panels. So from the basis of this article was saying less research and innovation is actually being done to make panels more efficient and make them more efficiently. And that may well, again, Emmanuel may come on to this later, but also in terms of Charlie's talk later on, in terms of the waste streams that come out of existing panels and future panels, what's the implication for that? Are there other paybacks we should look at? Well, carbon, yes, absolutely, possibly. But I would suggest, because I've been asked to provoke a debate, it shouldn't be the local carbon print. It should be the local carbon print, not the global carbon print. So we shouldn't be looking, I think, at the embodied carbon of what is your average PV on the planet. It is, well, where does this particular panel come from and what's its footprint? Equally, I think there's a strong argument within the UK to say we should be looking at the carbon emissions footprint of the power that we get from PVs, not in terms of the electricity, because in Scotland, that footprint, that carbon abatement benefit, in a sense, is shrinking with the average electrical emission factor of the grid. Should we be looking at the fuels it's displacing? And that way you can make an argument that if you build a very efficient building and you put some PVs on, your PVs are helping somebody else remove a gas boiler. And if we don't have incentives to still keep putting some PVs on roofs, then how are we going to provide the electricity for other people to remove gas boilers? Is there anything else we should be thinking about? Yeah, toxicity. And again, it might well be that Charlie and Emmanuel pick up on this in their talks. I don't know what the answer to this is, what the embodied toxic load of a PV panel is relative to, again, the fossil fuels that we're displacing. Cost, well, yeah, obviously cost, and yes, I will come back to that very shortly. I've only got about another 2 or 3 minutes to go, so I'm nearly done, you'll be pleased to hear. I think there is more. What's the embodied economic benefits? So this is questioning, there's certainly a value in creating an industry for people to manufacture PVs and to supply them and to install them. It is creating jobs. But are they good quality jobs? Are they high value jobs? Is the economic benefit being well served, if you like? So that could be a positive or a negative embodied attribute. You know, you could argue the economic benefit of purchasing and installing PVs is not dissimilar to carbon sequestration of using timber in buildings. It's an activity that's happened which in itself is actually of benefit. Still more. What's the embodied opportunity costs? Again, few people talk about opportunity costs, but this is, well, if people weren't in those industries making PVs, could they be making something else that would be more beneficial? Again, it could be a positive or negative attribute. I'm not suggesting I have the answer to this, but I think it's a question worth worth exploring and bearing in mind if you're in the position of specifying PVs. Only one left, you'll be pleased to know. What's the embodied social benefits? And this is a headline that I saw just the other day. What are the conditions of the people who are making these PV panels? Would you want to be making them? The answer might be yes. Again, I don't know the answer to this. I'm just picking up on stuff that I'm reading, the discourse about the manufacture of PVs and many other things. Now, you might say that these are all very difficult to assess. I've known people who've gone quietly bonkers trying to do life cycle analysis on carbon footprints. Hopefully Emmanuel hasn't done that yet, and he'll be very illuminating. But yeah, where do you stop? You can keep going on forever. But the answer is probably simpler than we think. Just follow the money. The money always tells you who's doing what and why, and who's getting the benefit out of it. And like I say, that might be a positive, might be a negative. So hopefully that has spurred a few thoughts, got you thinking about more about what is actually involved in, we're talking about PVs here, but on some levels it's any product or any energy saving, energy efficiency product. What are all the ramifications of making that, transporting it, installing it, and eventually decommissioning it and either recycling it or sending it for waste? So that's me.
Thank you, Richard. That's great. You don't even need my prompt for 5 minutes because you said it yourself, it's coming in. That's really good timing, as well as such a provocation of our thinking. And I did actually forget to say, put questions in the chat as we go along. To chat to each other as well, but also at the end, it will help us, prompt us all to think back and chat along those lines. So how it will work is when we get to the end of the three speakers, I'll pick up on the chat stream, as it were, and maybe combine or pick up some questions, maybe invite you to turn on your microphone and have a chat as well with the speakers as a discussion to end the session. So that's how it's going to work. So keep your chats, keep typing your questions into chat. And I would like to invite Emmanuel now to come to the front, if that is possible, and start his talk. Emmanuel.
Okay, good evening. I'm just going to share my screen now. Okay. I hope everyone can see my screen clearly. So my name is Emmanuel Shitu. In this presentation, I will be talking about our life cycle analysis can be used to critically assess solar panels, well, specifically for solar PV as a case study in this conversation. And yes, I will be pointing out, making some points as to what Richard has mentioned earlier. So some of those numbers I'm quite familiar with, so I'll be talking about, well, I'll be mentioning that in the subsequent slides. However, before diving down into the presentation in details, I would just like to introduce myself. I currently work as a postdoctoral research assistant at Swansea University. Specific essentially is a center that involves in research of technology and full-scale demonstration of active buildings that are able to generate, store, and release energy from solar energy source. So my role within the team that I work for essentially is conducting life cycle analysis of these technologies, specifically battery storage, and understanding the material and manufacturing processes of the battery energy storage. I recently defended my PhD thesis in February this year, of course, during the lockdown, during which, from the period of 2017 to now, I have contributed scientifically to operational energy savings and life cycle environmental impact of retrofit solutions for residential buildings. And I think Richard actually made a mention about how some of the solutions, what are the consequential benefits of integrating some of these solutions, such as PV or maybe just insulation within our building. And then finally, well, that more experience of myself, but I'm also a Marie Curie alumni, during which I worked for some months in Italy, conducting performance analysis of solar energy systems, such as high concentrator photovoltaic systems. So this is quite specific for regions such as Sicily with high solar radiation. Okay. Finding it hard to, so now let me go down. Sorry. Okay, there you go. So before looking at the PV case study, the question is, we need to understand what LCA actually means. So what is life cycle assessment? In simple terms, is the systematic analysis of potential impacts of products or services during the life cycle. And why do we use this? Within a business, it can help to reduce costs, reduce energy use and material use, and also within the 2050 target, it can help us to achieve this target of net zero greenhouse gas emission by 2050. The key capabilities are that, aside from assessing the environmental impact of product system, is identifying the hotspots within a product system, and I'm saying product system deliberately, which I'm going to talk about later, and areas of potential improvement, and also how we can explore future scenarios or future changes scenarios, such as further integration of renewable energy systems within a national grid. What is essentially the environmental impact of that? Because this will perhaps be displacing some some fossil fuel energy systems. So what is the environmental benefit or the material cost of that? So how does LCA works? Just a brief overview. The different life cycle stages usually will start from raw materials extraction, so resources, which is within the life cycle inventory there, through to manufacturing processes, consumption, energy use, and also recycling. That's if you include this within your product system. And then these emissions are what we call a life cycle inventory, such as if we look at global warming specifically, we have greenhouse gases, which include carbon dioxide, methane, and well, nitrous gas, and other compounds such as chlorofluorocarbon, and these emissions are then aggregated to what we call impact potentials. In this talk, I'll be looking at global warming, specifically global warming potential. So all of these emissions are aggregated to what we call global warming potential. The international standard of LCA are these conjoined standards, which are 14040 and 14044. Essentially, it involves 4 stages of conducting LCA. So the first stage, goal and scope definition, is defining the aim, the product system boundary, and the functional units that is being analyzed. So for example, PV is deliver 1 kilowatt of energy or electricity delivered, as an example. Inventory analysis is when you analyze the material inputs, the energy inputs into the system and being aggregated into impact assessments, such as global warming potential. And then the interpretation depends on what the person conducting the analysis is intending to do with these results. A recent report was recently published by International Energy Agency on the role of critical materials in clean energy transition. And in the report, it shows that crystalline silicon is expected to be dominant PV technology as we transition towards net zero global warming by 2050. And with some technology such as perovskite that is going to gain a significant share of the global market. So to that end, because silicon PV, crystalline silicon will be involved, I will be showing you some key results of the environmental impact of crystalline silicon PV. Why? So a key question to ask is, why do we need to conduct LCA analysis of PV? So what I've identified two key reasons here: understand the implications of global production shift to China. We've seen a gradual shift from to global production to China from 2005 to 2019 now, of which China holds about 71% of production globally. And of course, the goal is to critically assess the environmental impact of the raw material of the production of PV from cradle to grave, which is essentially from resource to end of life. So as Richard mentioned earlier, conducting LCA can be quite tax. It's an heavy task to do. So it's important to be able to define what we call system boundary. So this is just a generic system boundary for a crystalline silicon PV, which starts with silica extraction and then and processing to the manufacturing or processing and then cell manufacturing, and then to module manufacturing, which is then transported to the site, which is then from which it is installed, and then to operation and maintenance. Now, there is another case that could be included here, which is end of life or recycling. This I've decided to exclude that here because of lack of data or methodology. Well, literature essentially. I think Charlie will probably touch on this later on. How does solar PV fare with other renewable energy systems and non-renewable energy systems? Solar PV are actually the environmental impact in terms of global warming potential is significantly lower than non-renewable energy ones, but slightly higher than hydropower, wind and nuclear energy. This figure here shows some comparison in global warming potential of different technologies, with the ones on the right, which includes triple junction solar cell, gallium, indium phosphide, and so on, having lower environmental impact, while silicon actually has higher environmental impact in terms of global warming potential. So it is important to understand where the environmental impact of the crystalline silicon PV is actually coming from, and LCA would help us to identify some of the hotspots. So this figure here essentially shows, so the figure on the left-hand side shows the comparison of modern and reference monocrystalline solar PV. So what do I mean by that? So initially, I mentioned the transition of global production from Germany to China. So in 2005, we see the global warming potential of PV being close to 90, but then dropping by almost 45% in 2015 for PV made in Germany. And this is essentially because of technological improvements, which are key as we move forward in terms of improving efficiency of manufacturing process, and also increasing recycling within the manufacturing process of PV systems. In 2015, the impact in China is slightly higher than that of Germany, and essentially the reason is because of the figures on the right-hand side, which shows the share of energy consumption. In Germany, there is a higher share of the energy mix. There's a higher share of renewable energy consumption within the German or Europe energy mix, whereas in China, there is less of that. And there's less of that in China, and that then results in higher environmental impact of PV being produced in China. So some more figures, because they essentially, this is what LCA is about, showing where the impacts are coming from. So on the left-hand side is the graph of monocrystalline PV, and on the right is multicrystalline PV or polycrystalline PV. It shows that the main hotspot is coming from the production of the PV. If you look at the module itself, and silicon wafer manufacturing process being the highest within the PV manufacturing. So which then beckons the question as to how can we then improve the impact within this manufacturing process, which then leads us to what are the key manufacturing processes that are being used in China, and one of the key ones, and how can the energy mix, for example, be improved such that the environmental impact or at the production will be addressed and mitigated. An additional slide here, an additional figure here is showing how we know that the penetration or the integration of renewable energy system into the grid requires storage. So as we increase the amount of renewable energy, so does the required amount of storage is required. And this figure is essentially showing that even after including the storage, the environmental impact of PV compared to conventional thermal, such as natural gas combined cycle or diesel generator, is still significantly lower than the conventional technology for different solar radiation levels. So for example, the 1,000 kilowatts per meter squared year for UK is also a representative of Scotland if the PV is at an optimum tilt angle. So this static and why we see a slight increase in the environmental impact of PV due to the energy storage, in overall, it's still significantly lower than conventional thermal system, which is where the discussion as to what is the system boundary that you need to include. You need to just look at PV or look at PV and storage, or look at PV storage, and then compare to the grid or the energy system that the PV or the renewable energy is displacing, in order to have a bigger picture of the environmental impact, benefit, or cost. I think Richard talked about the energy payback time. These are based on literature data. So the PV, I think Richard mentioned 4.5 years. So that is right around there for PV. And for PVT is photovoltaic thermal system, so produces electricity and thermal energy. We look at, because of the high efficiency, the payback time is 1 to 4 years, which is quite lower. For greenhouse gas emissions payback time, this is actually an area that hasn't really been looked at a lot in literature. For PVT, we see a greenhouse gas payback time of about 1 to 15 years, and we expect PV to be either slightly higher than that, in that range. And this shows positive news in terms of, if we're looking at the life cycle of a PV of 25, 30 years. So about 50% of the time, hopefully we can get the greenhouse gas payback time. But further study is still needed in this greenhouse gas emission payback time. So just to round up the key conclusions that I can draw from this presentation, from this research, is that the key hotspots in the life cycle of solar PV is attributed to PV production, mainly in silicon wafer manufacturing and its upstream process. However, so talking about the previous capability that I mentioned is then understanding that if this is the hotspot, how can we then improve this? So one of it is essentially in technological improvements and manufacturing processes. I've seen global warming potential reduce by 45% for PV manufactured in Europe. And this is essentially as a result of when I mean internal recycling and energy efficiency, is internal recycling during the manufacturing process of silicon wafer, and energy efficiency of PV increasing over the time. I think triple junction solar cell, for example, in the lab, efficiency have reached about 40%, although the operational efficiency, I think, is about 25 to 30%. And understanding that there's a global shift in energy production, understanding that there's a global shift in to China in terms of global production, it is important to the future of environmental impact is also dependent on the energy mix of the Chinese energy mix. So, however, it's important to also point out that over the years, the Chinese energy mix has have a decrease. The renewable energy share is increasing. Of course, the non-renewable share is decreasing. So hopefully, there is the global warming potential of producing PV in the future as the demand of, as the integration of renewable energy increases, we will see a drop in global warming potential due to improvements in energy mix. Which brings me to the end of my presentation. So I think I've mostly been showing, I hope I've been able to show how you can use LCA to understand environmental impact of solar PV, well, not just solar PV, but any products and services that you're hoping to use or produce in the future. Thank you.
Thank you so much, Manuel. That is very illuminating and clear. It's also packed full of information, shall I say. One thing I forgot to ask the speakers before the talk is if you'd be able to share the slides with us afterwards, so that we can share people.
Yeah, sure, absolutely.
This because we could, you know, for those who are in attendance here, if you're anything like me, looking at the slides, go, oh, there's more information, and then it's gone. It'd be great if we could have the slides.
Yeah, I can definitely provide that, but I hope I've been able to show the
it's great, really great. Yeah, and Richard is saying he's happy to share slides as well. That would be great. Without further ado, we have Charlie Farrell, who is going to take us along this journey to discover more about all these raw materials and resources and what we're going to do with them, all this manufacturing process into making this PV wafer obviously is causing much concern, including how we recycle them. So, Charlie, over to you.
Thanks very much, Glo. Okay, so everyone, I'm just going to say thank you to SEDA Solar for having me to speak today. I'm just going to run through my presentation. So my name is Charlie Farrell, and I am currently a PhD student based in Northern Ireland. So I am registered with Queen's University Belfast. Now, I also work for a department, Southwest College in Northern Ireland as well, which I'll get on to with some of our links in Scotland. If I can get this thing moved away. Yeah, okay, right. Control panel. Okay. Okay, so this aside. Okay, so as I mentioned, my name is Charlie Farrell, PhD student based in Queen's University Belfast. I'm currently working with a local college in Northern Ireland called Southwest College that are involved with lots of European projects and also involved in a lot of renewable energy projects as well. So I am a PhD student on a project called Renewable Engine, which is to facilitate the innovation gap between academia and industry, so company sponsors. We are partnered with the Research Catapult in Strathclyde, the Advanced Forming Research Centre, with some other partners down in the Republic of Ireland, the Institute of Technology Sligo, and again, Southwest College and Queen's University Belfast. So my PhD is looking at effectively PV recycling. So I've been looking at first generation PV, so mono and polycrystalline panels. So my talk outline is just going to run over a few points, and I'll also include some supplementary material as well. So some of the papers and things that are quoted, they're all open access, so anybody can read them. Whether you're from academia or industry, you'll be able to get access to it without needing a university logon, which I'll include at the end of the presentation. So the talk outline, looking at legislative drivers for circular approaches to recycling PV, the scale of the PV waste problem, design specifically of first generation PV of crystalline silicon PV, the properties of the encapsulant polymer that's used in PV, which is linked with being the most challenging step to recycle, the energy inherent in PV weight percentages of constituents in PV, thermal analysis, hierarchy of sustainable development goals, some circular economy concepts such as butterfly diagrams, and material and energy flow analysis. So first of all, some of the legislative drivers behind recycling of PV. So PV modules were included in the Waste of Electrical and Electronic Equipment Directive in 2012, making it law as of 2014 that anybody that manufactures the panels or supplies them is responsible for their end-of-life management via a fee to the European Union. So PV modules, when are they considered end-of-life? So the general definition of an end-of-life module is when it drops below 80% of its quoted wattage at the time of manufacture. It has a lifespan of approximately 20 to 25 years, which is indicated by the manufacturer's guarantee. And here on the left, you should be able to see my mouse cursor. I have the waste management hierarchy diagram. So obviously at the top is the most preferred option, which is indicated here on the right, the prevention of waste or particular waste stream. And then down below, we have our least preferred option at disposal. So what I've highlighted in blue is currently where I believe the PV industry is at in the recycling and energy recovery stage, which I'll get into in a second. And then the WEEE directive, I've just included their logo in the bottom left there, which you would see with general laptops and mobile phones and things like that as well. So the scale of the PV waste problem. So we have two diagrams in this slide. The top comes from an IRENA report from 2016. And there's been an estimation that by the year sort of 2050, there'll be 60 to 78 million tons of PV waste in circulation. And then the bottom diagram comes from a Fraunhofer report in 2016, 2017, which indicates the market share of PV. So obviously my project and my work is outlining and looking at first generation PV, which is monocrystalline and polycrystalline panels. Now, over that 36-year period between 1980 and 2016 indicated in that diagram, first generation PV is averaged about 80 to 90% over that 36-year period. So the design of crystalline silicon PV. So I've included an exploded diagram here because PV modules, they include a lot of different types of materials. So they have rare and precious metals, they have glass layers, they have polymer layers, they have metals included, and then obviously electrical connections as well. So what I've included here, I've included basically a color diagram of the different layers to look at the EVA encapsulant. So the EVA encapsulant has been linked to be the most challenging stage to look at recycling PV, because that encapsulant layer obviously encompasses the entire silicon solar cell, which again, Emmanuel had mentioned about the life cycle energy in his presentation. So the problem effectively is being able to remove these two plastic layers to be able to be left with your metals and your glass fraction later on in the process. So there is a current method being used in industry, which involves the crushing and shredding of PV modules, which effectively will break up the silicon solar cell. And then obviously to recycle that particular fraction or that particular constituent, you have to look at the likes of hazardous chemicals. And you also have to look at the idea of resmelting the silicon once it's been cleaned with hazardous chemicals as well, to be able to form more sort of silicon ingots. And then obviously energy employed to cut the ingot to make cells again. So currently the main like industrial type of recycling focuses mainly on the aluminium frame and the glass fraction. There's a reason for that, which I'll get into in a second. So the ideal scenario when looking at recycling these panels would be obviously to look at recycling the silicon solar cell intact, if at all possible. And I'm just going to run through some research innovations later on in the presentation as to, you know, proof as to how these can basically be recovered intact, and obviously with the likes of electrical efficiency and stuff, they can be reused again for remanufacture. So as I mentioned in the previous slide, I mentioned about the first step is effectively the removal of EVA, the encapsulant that's used in PV modules. It's been the industry standard since the early 1980s. They used to use a polymer called PVB, polyvinyl butyryl. The solar grade EVA has roughly 33% vinyl acetate content by weight. So the vinyl acetate part of the polymer is this section here, where you can see the letter M. And then obviously 67% ethylene, which is over here. So EVA, polyethylene vinyl acetate is the full chemical name. Again, my background's in chemical engineering, so just bear with me. This is a bit of light chemistry here. So yes, it's been proven to be the most difficult step to recycle PV. And it's been used in the industry specifically for two reasons. So one, it's cheap, it's very affordable in the manufacturing process. And two, it has excellent adhesive properties to the front glass layer and the back sheets used in PV modules. So there's multiple types of recycling that can be used for PV modules and that have been reported in literature, in academia, and even in some industrial reports as well. So the likes of acid etching, organic solvents, shockwave recycling, and thermal decomposition. There's significant drawbacks to some of the methods, like the likes of acid etching and organic solvents, where there's a high cycle time, but also hazardous wastes that are generated, and emissions as well. Shockwave recycling, similar to the mechanical method that's used in industry currently. Again, it basically crushes the module. So it breaks down the silicon solar cell. You don't remove that as an intact piece. And then there's obviously more energy that has to be used basically to bring it back to virgin status, to go back into the manufacturing process. And one of the methods that's been looked at recently that I'm specifically looking at in my PhD is thermal decomposition. So it's not combustion that I'm looking at, it's pyrolysis. So it's effectively looking at pyrolysing the PV modules, or specifically cells in the module, to be able to remove the plastic encapsulant, the EVA layer, to effectively recover the silicon wafer and the other contacts, such as rare precious metals, like the likes of your silver interconnections and different things like that. So there was a report in 2018 from the International Energy Agency, which outlined chemical and thermal treatments to be superior than that of mechanical methods. And again, as I had mentioned earlier, conventionally PV modules are recycled via a physical treatment, such as crushing and then milling. That's done by an outfit called PV Cycle in Europe at the moment. And I'll talk about them in a couple of slides ahead. So the mechanical method's ideal for high throughput and manageable with current PV waste flows, but disregards the energy intensive process needed to form the silicon ingot, wafer, cell and module, which again Emmanuel had briefly touched on as well. And another thing to mention as well is the emissions that are produced in the manufacturing steps, such as silicon production, are not necessarily considered when you're looking at physical recycling methods. So one area of our work that was published in 2019, looking at specifically the energy inherent in some of the constituents in PV modules. So we looked at specifically used PV modules and looked at pyrolysis and basically calorific studies to look at the energy in the waste plastic. So we know that waste plastic can be used for energy. It's a fairly mature process with regards to pyrolysis. It's been done, you know, with lots of different plants around the world even to date. But what we wanted to look at was specifically that EVA layer, which hadn't necessarily been looked at in literature. We got gross calorific values of the used encapsulant, and we compared it to virgin grade EVA as well to see if there was much of a change, and the change was quite negligible between the used EVA, which is UEVA and BEVA here, then polymers, and they were quite high and comparable to the likes of biodiesel and home heating oil, which isn't surprising considering it's basically a hydrocarbon. So it consists of, you know, carbon, hydrogen and oxygen molecules as well, and petroleum based. Looking specifically at weight constituents of PV modules. So this is just a part of a table that I included from our review paper that was published last year. Looking at different sources on the different fractions or constituents in the PV module. The weight percentages of the glass and the aluminium frame are quite high there for two different references that are, I think they're about seven or 8 years apart, I can recall. But what I wanted to highlight there specifically with them two constituents is that the annex that talks about the targets for the Waste of Electrical and Electronic Equipment Directive. As of sort of August 2018, there's a target on 85% that should be recovered, and 75% should be prepared for reuse and recycling. If you look at that percentage and you add up the glass and the aluminium frame, you can see that that actually meets that threshold. So the likes of the other materials, like the likes of the silicon cell, although it only contributes a very small amount to the actual weight percentage of the module, it doesn't necessarily have to be included to meet them targets. But again, considering the amount of energy that's required to make silicon wafers, when you're looking at something like the Stchewalski process, which Manuel touched on in one of his figures, I believe it runs at like something like 1400 degrees centigrade. So the energy that's required even in that process is extremely high, not to mention the amount of emissions that's generated in that process as well. Now, Europe is sort of the only jurisdiction that does have a clear and regulated framework for the recycling of PV. However, there's a bit of a pitfall with that with regards to modules are collected with the outfit PV cycle, and then they're usually distributed to one of the 350 specialist recycling sites in Europe. And there was a great case study that was included in one of the Fraunhofer reports about 2 or 3 years ago, looking at the LCA of glass recycling plant in Belgium. And it showed that the basically, you know, the main fraction of the weight, which was glass, was obviously transported to this site in Europe, basically to recycle all this glass into cullet and things like that. But again, a lot of the LCA data and a lot of the recycling studies fail to mention the emissions that should sort of be included or regarded with regards to the transportation of specific constituents and the transportation of specific wastes to specialist recycling centres. So some of the most recent innovations, of two diagrams here, A and B. One's from a researcher called Doi on the left, and then on the right-hand side was Park et al. Basically, a few years ago, Doi had looked at organic solvents, looking at basically removing this EVA layer. And although they had got good results looking at recovering the silicon wafer, they noticed that the EVA layer and the plastic layer, when it was using organic solvents, it started to swell. So they needed something to basically suppress that swelling that created stress inside the cell to stop the wafer from essentially cracking or breaking. So they used types of binder clips to basically hold that mechanical pressure and allow the EVA to be removed, whilst allowing the silicon wafer to remain intact with good results. And Park et al., which is a researcher from the University of New South Wales in Australia, they had developed a mechanical fixture, basically a metal mechanical fixture where they looked at, on a cell basis, the recycling using thermal methods to remove the plastic, but also the light mechanical load to keep weight on the cell itself. And then there's little fins here in the top to basically allow gaseous diffusion to stop any sort of thermal stresses arising in the cell. And they were able to prove that they could get full cells out of the process using specific heating parameters. And then they tested them with rebuilt modules in a publication published in Green Chemistry, I believe, in 2018, and they were able to show that the electrical efficiency was 0.1% difference after the recycling process. So effectively what you're looking at is, although the manufacturer's guarantee is 20 to 25 years, if you're able to recycle these silicon solar cells and you're able to rebuild new modules, you're effectively doubling that lifespan. Because the problem is with some of the failure modes, you get that yellowing or the degrading of the EVA encapsulant, or over time it lets less light in, hence dropping the wattage down below that 80%. And then you're finding that these panels are being considered as end of life when they're not meeting the threshold. The other piece of our work, specifically looking at the pyrolysis of EVA, was looking at how cleanly it would delaminate the panels. So there was a lack of information regarding how far the reaction would go to completion and how much residual material you'd have left over, or you would have left over the post-pyrolysis process. So pyrolysis promotes clean delamination because it doesn't use oxygen. It's an inert process. So effectively, you don't have any oxidation or burn damage on the cell or the wafer itself. And as the pyrolysis process occurs, specifically looking at the EVA fraction, you're left with about 1% of the residual weight after. So it's a relatively clean process with regards to how far it goes to completion. And again, as I mentioned, the fact that it's made up of hydrogen, carbon, and oxygen, it's mainly hydrocarbons that you're making. So if it's used in a closed process, you can effectively look at harnessing the energy from these plastics, whether you want to use it for delaminating further modules in a concurrent or coexisting process, or if you wanted to use that energy elsewhere, which there was one particular study that it wasn't looking at pyrolysis, but it looked at combustion that used the energy from that to help heat water and utilities on site at basically a pilot recycling plant a few years ago. Some of the other polymers, like the likes of the back sheets, they're significantly more tricky to recycle because you're left with approximately about 20% residual weight left over. So this little red curve here is one of the back sheet samples. And if you read it over here on the left-hand side, you can see it's about 20% of the residual mass left over. So there's a bit of work that I'm currently doing at the moment, looking at that as well, with regards to obviously emissions and how to effectively recycle them. From the review paper, we were looking at specifically in the PV industry, how many publications had actually quoted and looked at the United Nations Sustainable Development Goals with regards to the PV industry. And we found that there wasn't a whole lot of literature out there. So what we did was we basically encompassed all the goals that we felt would be met if there was a proper recycling infrastructure brought in the PV industry, where it looked at concepts such as eco-design, where you could look at reusing or remanufacturing a module in the legacy panels. And obviously with the top goal at the hierarchy being responsible consumption and production, and then that would facilitate and feed into other goals such as sustainable cities, communities, decent work and economic growth. There's actually a report in the IRENA report which basically breaks down the economic value for the recycling industry, or looking at specifically recycling a PV, how much economic growth there would be in that area by the year 2050.
Charlie, a couple of minutes.
That's okay, no problem. The last couple of slides. So I'm sure some of you would be familiar with this particular diagram. This is basically a butterfly diagram, which is made famous by the Ellen MacArthur Foundation. We developed one of these looking at the different processes from the sort of extraction of raw materials and the mining stages all the way through to sort of looking at end-of-life treatment, landfill, and exportation of waste. So the ideal sort of circular model in this case would be repair and maintenance of PV modules to go straight back in for use, consumer use. But at the moment, with the current recycling methods in industry, with the likes of PV Cycle and how they mill down the modules and basically break up the silicon cells, you're finding that it's going down to sort of your C1 model there, where it goes into the effectively the recycling process again, right up the top of the manufacturing chain, where it has to go through the smelting, the cleaning process and this re-smelting process to basically make silicon ingots, and then having to go through cell processing again and the actual lamination process. So there's a lot of energy that has to be considered, as well as obviously the emissions with them subsequent processes when looking at the actual life cycle of PV systems. This is just my last slide here, really. So this is looking at, again, sort of circular models for the PV industry. So obviously with my work, I'm looking at harnessing some of the energy from the polymers included in PV. So scenario B and scenario C there are looking specifically at energy, whereas material is indicated with the black arrows. So my work is effectively trying to develop model C, where it's effectively using the energy inherent in PV modules to be used or recycled in further delamination of modules, or the heat effectively just being used again to keep the process heated. With this process, again, it runs a lot lower than the likes of the silicon manufacturing process. So the pyrolysis of the polymers has been proven that it can be carried out to completion at about 500 degrees C. Whereas obviously the silicon process can go anything up to 2000 degrees. When you're looking at the likes of the ARC process, it's like 2400 degrees C. Scenario B is looking at open loop energy recycling, which I mentioned previously. One publication looking at the combustion of or closed combustion of some of the PV modules and using the energy to help heat utilities such as water on site. D being your ideal circular economy, where all the material is effectively harvested and reused again for its actual purpose. It's not effectively downcycled. And module 1 is open loop material recycling, where some of the materials such as the likes of your aluminium frame would be used in sort of general aluminium recycling, or the glass layer would be recycled for general glass recycling such as cullet. And just this picture, just to leave you with this thought, you have the PV modules there sort of looking towards landfill and sort of stacking up. This is sort of the, this is the reality of what is effectively happening and going to happen in the future. And again, on the top right there from a Bloomberg article last year, looking at the recycling of wind turbine blades, which is another problem again. It's something that we have to consider. Although we have green options now, we have to obviously keep reiterating the design of these particular green sources and, how they're going to match up with the likes of more stringent targets as things go on, or as time goes on, like the likes of the Paris Climate Agreement, the WEEE, different things like that. And again, just as I mentioned, there is open access publications on the review of PV recycling, looking at all the different methods, both academia and industry, and some of the lab data looking at the energy characteristics of the polymers and the PV modules, published with the Renewable and Sustainable Energy Reviews Journal and Nature Scientific Reports. So they're open access, anybody can access them. If anybody's interested in any further reading, I've just included as well some of my contact information if anybody has any more questions that maybe isn't answered today. And thank you very much for listening.
Thank you so much, Charlie. That's really great and all-encompassing almost. I think some of the questions came up and then you answered them. But it's really good to have this in-depth review. I would invite all the people who wish to turn on their videos and join in with the chat and so on. But to start off, I would just like to say, especially from Rich's original provocation, there are things about the supply and demand and all the tricky things about what we have to think about, social and all sorts of aspects. We are actually going to have future seminars dedicated to the storage of both heat and electricity in terms of our supply and demand, the grid capacity and battery use and all of that as well, in fact, 2 separate seminars. And in fact, this seminar is also, well, partly was in the pipeline anyway, as well as I think is Jacqueline, I don't know if she's here today, but prompted us to say, well, look, we need to look at the LCA and embodied carbon and raw materials in PV panels when we're talking about installing solar panels last year. So if anybody, anybody here, everybody here who knows me well enough of organizing CPDs and things like that over the years will know that if you pop in the chat other suggestions of future seminars you'd like to hear about, then I'll definitely go about organizing lovely people like we have today to talk about specific topics. So if I don't actually pick on your question, it's not because I've ignored your question, it's because we probably have an entire seminar coming up to address that specific question. But I'd like to start with John's question on legislation and how European countries and different countries is treating recycling and the different lack of regulation even is impacting on our recycling. Charlie, what do you think about that, and how about all the gas emissions and all the toxic stuff that is going into the atmosphere as all the chemicals are being used?
Yeah, so with regards to John's question there, where he mentioned about international ban on PVs under WEEE since Brexit. I'm not too sure how things are exactly with Brexit, but what I can say is I know that in the past there was a massive issue with the exportation of waste to countries that didn't necessarily have a strong recycling infrastructure. But there has been, I know as Richard had mentioned China, there has been reports as of sort of the last 2 or 3 years where China isn't taking any electrical waste in anymore. With regards to other countries, I'm not exactly too sure with exact figures. With our review paper, we had basically taken, I think we had done it on a continent basis, where we had percentages that was outlined in other papers. But with regards to an international ban and Brexit, I'm not exactly sure what the situation is now with that. So I wouldn't be confident in answering that honestly, because I honestly don't know. And every country, well, obviously the European countries will have, their own dedicated infrastructure, but some of the other countries, that electronic waste or PV would be sent to, they obviously have their own or lack of policy.
Yeah. So in terms of like the end of life classification, do you think if we extended it to, when its output is down to 60% instead of 80%, or whatever percentage would be actually a realistic one to actually lower it so that it's as a cross point of the curve, as it were?
I was just scrolling there. I just saw what Richard had said. In my opinion, I never fully understood that idea of 80%, dropping 80% of its initial wattage quoted at manufacture, because obviously if the panel is still creating electricity, if you're a consumer, if you have PV panels on your roof, if you're still creating electricity, you're effectively getting your service out of that. And the whole idea, when you stand back to I know obviously there's a lot of definitions out there in academia and industry when you talk about the term circular economy. Actually, it reminds me of a paper in Recycling, Resources and Conservation, where there was 117 definitions quoted on the circular economy alone. But if you look at, something like the likes of the Ellen MacArthur Foundation, and they mention about, circular economy, you're specifically looking at, the service, not necessarily the materials. If you're looking at merely from a material perspective, if you are a PV consumer, I don't think you should be worried about end of life status if your panel's at 70% and it's under 80% and it's classed as end of life. I think that was probably a target that was probably put on panels by the likes of PV Cycle in the past. Again, I can't see why people would be worried about having a panel that's still creating electricity for them if they're more concerned about getting their electricity in a green way.
I guess it comes to a point where it generates like 30% of the original. It doesn't cover
diminishing returns, that's going to happen anyway.
Yeah. Richard, you were going to say something.
Yeah, I was just going to contribute to that. I mean, I completely agree. My panels, if they're producing 70% electricity, and unless replacements are so inexpensive and so more efficient, why would I take them off? But having said that, is there a danger? Unfortunately, I'm now old and very, very cynical about most things. But is there a danger that there'll be a temptation to get around some of these the sort of WE directive and recycling targets by actually a market emerging in second-hand repurposable PVs? So they actually get dismantled, they get taken off roofs and exported as, okay, they're not particularly efficient anymore, but you can have them for a cheap price or almost nothing because you're going to use them. But actually they just get, or indeed they come with a dowry. You know, we'll give you money to take them away. Please connect them up in somewhere else. And actually they then just get turfed into a corner or a very large field, as it might be.
Yeah, that's exactly right. I think, again, as Emmanuel had said earlier as well, when you're conducting, like LCA, or you're looking at these system boundaries, it's very hard to put the boundaries in place to control everything. But I think one of the main things with PV is obviously the transportation and the transportation of the waste. In particular, I'd encourage anybody to take a look at that Malta glass recycling report that was included in one of the Fraunhofer reports a few years ago, because like I said, they transported glass waste and then the other constituents were sent to landfill. And, it was specifically designed for glass recycling and it was transported. And with glass obviously being, the significant contributor in terms of weight of the panel, there's obviously going to be more emissions to transport that based on distance or where it's going to. And I know that PV Cycle have outlined, they've said they've got about approximately 350 sites around Europe. Depending on the logistics of things, if you're going from one end of Europe to the other, it's not really, it's not really green when you look at it that way.
No. Has Emmanuel got anything to add on this in terms of life cycle analysis? If we increase the lifespan of the actual panels, that must have an impact, right? Oh, you're muted.
So increasing the life span of the PV system actually does have influence on, for example, reducing the environmental impact. So for example, a case study which I actually looked at is a high concentrator photovoltaic timer system. I looked at a case study where I assume it is the life cycle is say 25 years, and of course increasing the number of years of course reduces the environmental impact. What it does is that it actually increases the operation and maintenance impact, but it's slightly higher. So that it's actually beneficial when you're looking at expanding or increasing the life cycle. Yes.
Yeah. I think a question for Richard. Neil is asking, if just any local person ask about payback on a standard solar PV cell or panel, what would you give us a simple answer? I suppose we've kind of talked around it. There's no real simple answer. What do we say though? I mean, I will start with Richard, but we'll go on to the other speakers as well.
I think it's down to your personal motivation for doing it, and are you putting on an installation? Yeah, I mean, are you installing them for them, simply for the environmental benefit? Are you installing them as part of getting demonstrating compliance for a new building or something like that? It's very, very difficult. Because the numbers we've been talking about, and Emmanuel hit the nail on the head. If we continued to import PV panels from China, and their carbon footprint of their manufacturing in China drastically decreases, which it may well do over time, then actually the numbers come back round again, don't they? Suddenly they do start to make well, you know, they make sense again. So yeah, it's very difficult. I think. You know, I've swivered backwards and forwards on this several times, and I'm still of a mind that they are necessary because we need more zero or low emissions electricity to break our dependence on fossil fuels, as I said before. But there's also, again, flip side of that is, even if we make grid electricity more efficient, if we're creating more electricity anyway, the overall level of carbon can still continue to rise. So like any manufactured process, you get the sort of Jevons paradox, where the footprint or the cost of it goes down, but because it goes down, it becomes so much more affordable. You just make vast amounts of it, so the total quantum still goes up.
Yeah. So to follow that up, Rich is asking Emmanuel about this the EPD, the Environmental Product Declaration. You know, so that the client knows about embodied energy of the product. Should the benefits of lower carbon solar PV be better publicized?
The EPD, I think, should be encouraged and should be declared, because I think, in my opinion, it will drive technological advancement between key PV producers or suppliers, in terms of having a better environmentally friendly product.
Do you think it's an accurate representation of the, you know, thing in terms of the life, the analysis of the whole life of the PVs?
Yeah. So this is where standards have to be followed. So this, just to clarify, the numbers that have been published in literature, I don't think these are uncertain, and there's no way to actually say these are actually really accurate. But what it does point out to is these are potentials, where after following certain standards, we'll be able to quantify what the potential of a given product will be. So in order to standardize the environmental product declaration, it's important to be able to follow a specific standard of analysis to then set, which would then be good for comparison. For example, there's a lot of study, because of the LCA study on PV already, and there are different functional units. They looked at 1 meter squared of panel, kilogram, which can be very difficult to compare, because you choose, the bias is that you might want to choose the functional unit that gives lower environmental impact, but it's important to be able to standardize this and say, okay, for every 1 kilowatt hour of electricity delivered or generated, what is the environmental impact? And I think there should be a standard to be able to conduct the EPD.
Yeah, and you think it's good enough to doing its job, as it were?
Well, well, I think it's a good starting point, and then we monitor the progress as we go along. And I think also establishing policies in place that would also guide this documentation are important. I don't think other ways of improving these is also refining data, because LCA are very data driven. So it's important to continue to update data from where it is actually coming from. So if it's coming from China, we update. If it comes from Germany, the Europe, we need to continuously update this data to get better representation. And of course, policies as well.
Yeah. So another question that came up, probably directed to Charlie, is that you know, we talk about use of materials and then burning off this EVA, and then it releases hydrocarbons. You know, is that still, you know, environmentally friendly, right? You know, and we're looking at lacking raw materials. You know, running out of silicon or whatever it is that there are, you know, raw materials that we're going to deplete of the earth. And Is there an alternative way of making this, you know, instead of encapsulating in plastic, but in renewable or more sustainable plant materials or something like that? Is that something that is being looked into?
Yes, well, there's been some academic studies that have looked at using other encapsulants. However, the general consensus with that is that it doesn't match the adhesive properties of EVA and also the transparency values with regards to letting light through to the cell. Again, that's two probably of three of the main reasons why EVA has been used for so long. Again, as I mentioned briefly in the presentation before, they did use a different encapsulant in the very early stages where they used polyvinyl butyryl, but EVA has been used since the early 80s. The problem with that is it's really an eco-design problem, because with regards to the PV module manufacturing, the actual materials used in PV modules haven't necessarily changed, but the amount or the percentage or ratios in terms of weight has changed based on how mature the process has got over time with regards to module manufacturing, with regards to, like, say, for example, sawing technology has advanced quite rapidly. So they use less silicon per cell than what they had used before. So at the moment, I believe solar cells are about 180 micron in thickness, whereas before they were closer to like 450 micron in the past. And additionally, with the likes of critical materials or critical raw materials, like the likes of, say, silver, that was used in like legacy panels, there's more of that used in older panels than there is newer. But again, it's still there in terms of the actual materials used. Just there was a few things there just that I had written down in between Richard and Emmanuel's presentations. There was one here that I didn't include. So here, like a researcher, Lou, had published between 74 to 75% of life cycle energy use of a PV system is in the module manufacturing stage. So that's quite significant. And then as well, here with regards to me mentioning silver there a second ago, silver, if you take the figure of 0.05%, and you're looking at that PV waste flow of 60 to 78 million tons by 2050, it equates to, 3 to 3.9 million tons of potential silver resources. So it's huge when you think about it that way, when you're looking at critical raw materials. And then another thing as well, PV Cycle, just one of their studies, they had claimed that recycling 1 ton of PV waste equates to an 800 kilo of CO2 equivalent savings and energy savings of approximately 8.5 gigajoules from non-renewable fossil sources. So it is quite significant when you look at it that way as well. But just the initial point when you said about the pyrolysis process, I think it's more, when I said it's an eco-design problem, I think it's more an issue that the panels obviously should have been designed where they could be, the constituents could be reused effectively. But because EVA, because of its nature of being cheap and having its adhesive properties and transparent properties, it has been something that I think the industry sort of shied away from. But with more people adopting and installing solar year on year, that 60 to 78 million ton that's quoted by the IRENA report will probably increase over time. And it's also, again, as I think Emmanuel or Richard had mentioned about that the crystalline silicon still set to be dominant market share in the future. Another report that would be quite beneficial for people to look at if they haven't looked at before is the ATR PV report, which changes every year. That's the International Roadmap of Photovoltaics, and its most recent report there states that crystalline silicon technologies dominant to its end of its potential data set, which goes up to 2027. So that's for the next 6 years at least. And that's not including, obviously, that lag time of the 20 to 25 year period or manufacturing period, depending on when them panels hit the actual waste stream or end of life stage where they have to be recycled.
Yeah. I'm aware of time, and we really want to sort of wrap this up, but I have a burning question I just can't stop myself from asking, is whether you think perovskites would actually help or worsen the equation, given that in the previous seminar we discussed perovskite, once it's become available commercially, could actually be produced locally because it doesn't depend on China for all, and less transportation and all that sort of stuff. So and yet it uses very different and other critical resources. Very quickly, few words from each of you. What do you think the balance shift would be, and do you feel hopeful about perovskites? Emmanuel?
First, me?
Yeah.
No, perovskites, I think they're an excellent idea. I think if they can beat that Shockley-Quasar limit in terms of electrical efficiency, I think that's definitely beneficial compared to the likes of first gen, which is capped at about, I think it's 24% is the physical limit, or 26% when looking at single PN junction. But I would stress the urge that if they are looking at adopting perovskites for, industry and industry installation or consumer installation, that they consider the recycling of them ahead of time, because engineering's always been an iterative process. Everybody who's engineered something or engineered a great invention, when it comes to looking at it down the line, if they have to modify it or they have to change it or they have to look at recycling it or its environmental impact, it's always more problematic at a later stage than doing it from the get-go when you're looking at thinking.
Do you know if they're looking at it at all at the moment?
I don't know. My knowledge on perovskite would be quite limited. Again, a lot of my work
Fair enough.
First gen, so I wouldn't know indefinitely about that. But I would be very interested to see. I think they probably would, considering there's been a massive citation and publication increase on PV recycling. I think between the last 5 years, it's been 51 times more than the previous period for PV recycling,
and therefore
with citations and publications in general. Yeah.
Manuel, what's your thoughts?
Okay, so in terms of perovskite, I think to what Charlie mentioned, increasing, I think the efficiency of perovskite says about 12% to 10% now. I think, of course, increasing this efficiency would help reduce or improve the environmental impact. I think up to date, the energy payback time is about 1 to 1.5 years, with a global warming potential of about, I think, 100, which is slightly higher than silicon, but with the continuous improvements in the manufacturing process. Say, for example, the coating of perovskite and roll-on manufacturing process would hopefully help reduce the environmental impact going forward.
And Richard, what's your final thoughts on this?
To be honest, I think it's a question that's above my pay grade. You've asked one that I don't.
Well, it's more.
I don't have a technical answer to.
Well, no more to do with like if the panels would be able to be produced in Scotland, for example.
Yeah, well, I mean, if we were producing panels in Scotland at the moment using Scottish electricity, and we exported them to China, then they'd pay back the carbon footprint in 2 months.
Yes, so you are positive in that sense.
Well, yeah. I mean, it's absolutely, and there's a general point here, which is as the economies decarbonize, everything that economy is producing is going to trend back to zero or near zero carbon. I guess the question is how quickly different economies do that. So we will continue for a long time to have all these imbalances.
Yes, I think we all know that this is not a very simple answer to any of these questions we've been asking all of tonight. So without further ado, I'm going to let you know what's going to happen next. I'm just sent you the links to some of the things that is coming up, which I'm going to share screen of. We've got further solar seminars coming up. We're going to talk about, as said before, talk about storage, active and passive storage, heat, battery, and also the grid capacity, and to talk about the best way to install these things, the more efficient way of doing so, what controls we use, how we make the users use things properly, and reduce performance gap as we do so. We also have the SEDA conference coming up, and the AGM, and on the 10th, I believe, Sandy Halliday is also speaking from Gaia Research, and oh gosh, the other name I had currently forgotten. David, was it Jimmy from Wellbeing Association?
Yeah, Jimmy Paul from the Wellbeing Alliance, who's he's the head of it. So he's going to really give you the lowdown where we can go to economically.
Yeah, great. Thanks, David.
Thank you.
And we're also having an Archifringe event where our chairperson, Catherine Cosgrove, is going to speak at, as well as folk from RIAS, as well as Construction Declare are going to speak at, to provoke further collaboration within the industry to look at climate action, to combat climate and ecological breakdown, and further chats on that aspect and see what we can do and take positive action. So the links of more details is in the chat if you are interested. And yeah, put your suggestions for future talks and everything in the chat, and I'll collect those. And for now, say goodbye. Thank you so much to all the speakers, and a big clap to you all. I know all the audience will be clapping, not that you can hear them. A lot of them said thank you to you already on chat. So I hope to see you again in other future sessions as well. We'll be inviting you as a thanks to our future talks as well. Thank you all. Cheers.
Yes, bye.
Thank you very much for listening, guys. Bye-bye.
And bye-bye from me.
Bye.
Thank you all soon. Bye now.